Hi, welcome to BC Video 11.1a, Part 1, Intro to Vectors.
Okay, I'm going to go through this very quickly because it's very basic. You saw most of this in pre-calculus, so it has been pretty well 2 years since you've seen this. Okay, we're only going to do two-dimensional vectors. If you might remember, in pre-calc you did 3D vectors, so our vectors are in a plane. A vector basically is a directed line segment. It does have a particular length. It's not a ray. That arrow does not imply that it goes on forever. The arrow simply implies that P is the initial point and Q is the terminal point. So it has a particular length, but it also has a particular direction. So the vector PQ, which is a one-headed arrow, not a two-headed arrow, but a one-headed arrow, and it's important that the initial point be in the first position, the terminal point in the second position. So the vector PQ cannot possibly equal the vector QP because they have different initial points. This is the vector QP, this is the vector PQ. The length of the vector is called its magnitude, and it's denoted by a double absolute value sign. Okay, equivalent directed line segments, which are vectors. Equivalent vectors have the same magnitude and the same direction. So for example, vector PQ and vector TR have the same length, so they have the same magnitude, and they're both pointing in the same direction, which at this point you can think of as, let's say, a 35-degree angle with the horizontal. A vector can be represented with a lowercase letter with the arrow over the top. Now, the textbooks are going to make it in bold print with no arrow over the top. Some books will have a double-headed arrow. I prefer to use the single-headed arrow. It's very hard when you're writing to make it bold print. It is a lowercase letter, and in other words, I could call this vector PQ and just give it a single name of vector V. So a directed line segment that represents all of the directed line segments equivalent to the vector PQ. So all of these could be called vector V because they all have the same magnitude and they all have the same direction. The direction has a slope component to it, obviously. The directed line segment PQ, where P is 1,5 and Q is -2,6, as you can see from here. First of all, the magnitude or the length of that vector is basically what we used to call the distance between these 2 points, which of course is the square root of x2 minus x1 squared plus y2 minus y1 squared, which in this case is the square root of 10. The length or the magnitude of a vector, of course, is always going to be positive. A vector is in standard position since all these vectors are the same vector in that they're all equivalent vectors and that they all have the same magnitude and the same direction. A vector in standard position means that you're specifically going to look at only the one whose initial point is the origin on the xy plane. So here's a few examples of vectors U, V, and W which are in standard position. Okay, we talked about this. Yeah, that's nothing new. So another way of writing a vector is to write it in what's called component form. Now, when you use these pointy brackets as opposed to parentheses, when you use parentheses, you're talking about an actual point. When you use these pointed brackets, then that's a vector in component form, and the x1 and the y1 represent the coordinates of the terminal point. So when you write this, it implies a vector with initial point 0, 0, and terminal point, and I'm actually talking about a point here, the point x1, y1. Okay? If we talk about a vector 0, 0, that means it has magnitude 0, it has no direction. It means it's simply a point because its initial point is 0, 0, because it's in component form, as is its terminal point. So the textbook will write that 0 as a bold print 0. I would write it as a 0 with a vector symbol over the top. And that's called the 0 vector. Equal vectors. Two vectors are going to be equal if their x components are equal and their y components are equal. The magnitude of a vector written in component form, since the initial point is 0, 0, the magnitude being the length is the distance between the 2 points, As you can see, because of the 0, 0 here, it turns out to be that the magnitude of the vector x1, y1 is the square root of x1 squared plus y1 squared. So as an example, here you would get 5. The interesting thing about the length of a vector, which is the magnitude of a vector, and other books call it the norm of a vector, is you don't get a vector as an answer. You get a real number which represents the length of the vector. Okay, now some of the questions will give you an initial point and a terminal point, and they'll ask you for the component form of that vector and the length of the vector. If you draw the initial point and the terminal point, 3, -7, -2, 5, you realize that to be in standard position, we would have to physically move this green vector until the point P was at the origin, because the initial point has to be 0, 0, and then we'd be looking for the terminal point. So if you look at what you're doing, in effect, is you're taking 3, and in order to move it up to this location and over to the left, you'd have to move it up 7, and you'd have to move it left 3. So basically you'll have to do the same thing to the -2, 5, which is move it up 7, and then left 3. Okay, so look at that point again. We're going to move it left 3 and up 7. So we'll have to take this point and move it left 3 and up 7. The way you can look at it is to put it in component form. If you look at the initial point as x1, y1, and the terminal point Q as x2, y2, it's basically x2 minus x1, comma y2 minus y1, which is the terminal x value minus the initial x value, comma the terminal y value minus the initial y value. So it's important that you start with terminal minus initial, not the reverse. Okay? So terminal x minus initial x, comma terminal y minus initial y. Of course, once you have it in component form, then it's the square root of x1 squared plus y1 squared.